Was your interest in big data and in knowledge, did that arise then as part of your thinking about what the connection machine could be good for? Or was that something that you had
That's what we built the connection machine to be.
Uh-huh.
It was good at big data. Some people have attributed me with coming up with the term big data.
Uh-huh.
And if it was, I think it could be, it came from the Laurie Anderson titled Big Science. Hallelujah. And it's big science.
Hallelujah.
So big data, always with this sort of little smirk, right, of Laurie Anderson's smirk. Big science, hallelujah. Big data, hallelujah. And the idea that we could put these together, information together to make something smart. It was a very different radical rethinking. There was before the connection machine, before thinking machines, there was a lot of ideas that you just had to be super smart to be able to understand language. Another approach was just have a lot of language and be a little bit smart. So a lot of data, little smart. And that got us so much further towards making progress towards the goals of AI. And that, I think, is what we ended up with this, with the search engines, the web, the internet, is lots of ideas and then doing little bits and pieces on top of it. I remember Doug Lennett, who worked at Thinking Machines, who built this wonderful system called Psych to try to map ideas by hand putting together a computer-readable version of the encyclopedia. Way ahead of his time. But he said that, wow, I went and used your system WAIS. This is before the web. And it's amazing. It actually works really well just by having a lot of data and being a little bit smart. And I think that's some of the tension. It's not right or wrong, but Thinking Machines, because it had the chutzpah to go and build a machine that cost millions of dollars that would be used by a single person, that would be something that you could do. You would be able to see the future. And the future turned out to be the future we're currently living in the early 21st century.
And that's interesting because I remember the programming paradigms at the time. The big boys, the Crays and IBMs and whoever was building supercomputers at that point were saying, this is ridiculous, you've got 1-bit processors, they can't do anything, you need intelligent processors, but the problem is when you have more than one or two of them, then it's really difficult for them to coordinate with each other. Therefore, parallelism is a concept that's doomed. There's also this Amdahl's law, which was proved to be erroneous, that the problem would grow exponentially as you're adding more adding more processors to the mix. So that really was, I think, the revolutionary aspect of Thinking Machines, saying that we're going to start out, so to speak, small with these 1-bit processors, and each one has its own data. So a data parallel machine, lots of information, maybe can only work on certain types of problems, but those are important problems like modeling weather or doing computer graphics or doing the sorts of searches that you're talking about, and then we'll see what happens. Now, I've heard that
just a moment.
Okay.
You can't be behind the camera. You're part of the picture.
Oh no, because
yeah. I get you. I get you. Come on. We get to make our own history here.
Okay.
Are you going to be in the frame?
Oh, I have no idea. I think so. I think I'm just barely in the frame, but whatever. So a couple things that I've heard from people is that, those days back in the 80s, people were saying it's impossible to write parallel programs. And then I remember talking to Rolf Friedrich, who said, well, it turns out if you bring up undergraduates learning how to serial program and then try and teach them how to parallel program, then it's difficult. But if you teach them parallel programming from the beginning, then They're like fish in water. They don't realize that this was supposed to be hard. Is that true? Is parallel programming being taught now? Or is it still mostly serial? I mean, my perception is from, Harvard CS50, Introduction to Computing, they're teaching like C and things like that, but it's object oriented, but it's all serial.
Oh yeah, we're still stuck. We built this machine that it took really, really interesting and smart people to think through how to do it. Carl Sims did amazing computer graphics. Creon Levitt, there was the guys that did colliding galaxies. Stephen Wolfram always thought this way. He just thought of the world as a pixelated world that evolved, and so it was innately a big cellular automata to him. But most people think of small pieces together, and it's in some sense the tragedy of thinking machines that we started out with 64,000 processors, and we got to these more and more clumped, larger scale processors. So if you look at how the Internet Archive or Alexa Internet or Amazon or Google are built, they're actually quite substantial. I mean, you can point to them, computers, right?
Yeah.
1, 2, 3, 4, you can count them, right? It's not like there's millions and millions of these things.
Is that true also of, for instance, Google's search farms?
Yeah, you can count them. And usually you design your algorithms by thinking of a federation of computers rather than it all being one smooth, smart memory. So in some sense, we haven't succeeded yet at some of the really brilliant ideas. There's been a legacy of why we got there, but there's still much more we can do. We ended up separating out the computer design and the manufacturing of silicon went to Asia. And so the design was still going on here, but and by having that kind of long distance, it just made it too slow. If we could integrate, one of the great things at MIT and even Thinking Machines, I was an undergraduate at MIT. I could design chips. I mean, what the heck? I mean, I designed a chip by writing a computer program that generated this outline of what the picture of the chip should be, and I sent it in email to Moses. It was a system that then a couple months later it came back a chip. I thought this was just the way the world worked. I mean, it's sort of like hitting print, and you get a chip. It's like, what a great thing! What an opportunity! It allowed us to as an undergraduate write a undergraduate thesis. Right? This is on how to design and implement a microprocessor, a completely different computer architecture. You could be built in a few months by an undergraduate. You can't do that anymore, and it's not because the technology doesn't allow it.
Really?
It's because we've screwed up our corporate structures and our the integration of how government funding works within our universities. We've blown it. So a lot of things were stuck, and the programming one is absolutely one of them.
So do you think there's an opportunity to then bring that manufacturing capability, especially for instance, as things become more robotized, mechanized, AI-driven, so that again you could have undergraduates sitting there and having the chips fabricated. The building next
I think
door.
that it's coming up from below. It's the maker movement. It's the I want it back, damn it. Enough of these stupid, large-scale, multi-billion-dollar, corporately run manufacturing units. Let's build it from scratch. And so we're seeing the invention wherever we can give the tools to people, and let's give more and more interesting tools. And maybe it'll be DNA sequencing and then composition that will be before the computers come around.
Let me check and see how it might not be advantageous to have me in this.
Oh, I think it's completely great.